In this video, we'll apply our general results for the asymptotic behavior of maximum likelihood, both under correct and incorrect specification, to the simple example that we started off with, namely the estimation of theta, the parameter of a Poisson distribution. Recall that the logarithm of the Poisson PMF is equal to negative theta plus y log of theta minus the log of y factorial, and thus taking the first derivative, we obtain minus 1 plus y over theta, and taking the second, we obtain minus y over theta squared. Recall, moreover, that we showed that for this example, the pseudo-true parameter, theta naught, is equal to the population average, the mean of y, and the maximum likelihood estimator is equal to the sample average, y bar. Using the formulas for j hat, k, and k hat from an earlier video, we'll now carry out the asymptotic variance calculations. By definition, j is equal to minus 1 times the expectation of the second derivative evaluated at theta naught. Here, theta naught is just equal to the expectation of y, and we showed that the second derivative of the log likelihood in this example is minus y over theta squared. Combining these two facts and simplifying, we see that j is equal to 1 over the mean of y. The sample estimate, j hat, of this matrix simply replaces the expectation with a sample average, and the pseudo-true parameter value theta naught with the maximum likelihood estimator. If we do that, again substituting the expression for the second derivative, and also substituting our estimate theta hat for y bar, which is what it equals in this case, we obtain j hat equals 1 over y bar. We proceed similarly for k and k hat. For k, which is defined as the variance of the first derivative, using the expression d theta of log of f is equal to minus 1 plus y over theta, and substituting theta naught for theta, if we simplify, we will obtain an expression for k that is equal to the variance of y divided by the expectation of y squared. And proceeding similarly for the sample average, we will find that k hat is equal to the sample variance, sy squared, divided by the sample mean squared. And here I have defined the sample variance to involve 1 over n rather than 1 over n minus 1, and that's because we're working with maximum likelihood, so we don't make the degrees of freedom correction that you may have encountered in your introductory statistics courses. So when you estimate a sample variance, if you want to ensure that that is an unbiased estimator, you use n minus 1 rather than n. Here we're not doing that, and that isn't really of any serious consequence, but I just wanted to point it out in case it gave you some concern. Now we're ready to check that the general theory we developed for maximum likelihood estimation does apply to this example and gives us what we expect. If the model is correctly specified, then we know that j is supposed to be equal to k by the information matrix equality. Let's check whether that's really true. As we showed on the previous slide, in this example, j equals 1 over the expected value of y. But if the model is correct, then the expected value of y is theta naught, because y is a Poisson theta naught random variable. Similarly, in this example, we showed that k is equal to the variance of y divided by the expected value of y squared. Again, that's from the previous slide. But we know that for a Poisson random variable, the variance is also equal to theta naught. So substituting theta naught for the variance of y and theta naught for the expectation of y, we see that a factor of theta naught cancels in both the numerator and the denominator. So k, too, is equal to 1 over theta naught. Just as the information matrix equality told us, j equals k, provided that the Poisson model is actually correct. And indeed, j inverse times k j inverse simplifies under correct specification, So what do we obtain? J inverse is theta naught. So we have theta naught times k, which is 1 over theta naught, times yet another J inverse. This gives us theta naught divided by theta naught times theta naught. 2 of those theta naughts cancel, and we're just left with theta naught. Notice that this is the expectation of y. So under correct specification, the theory that we developed for maximum likelihood estimation is telling us that the asymptotic variance will be equal to the expectation of y, namely theta naught. Now, what if the model is wrong? Well, in that case, our calculations from the previous slide still go through, but we no longer have equality between j and k, because the information matrix equality does not apply. In this case, j equals 1 over the expectation of y. So the inverse of j is just equal to the expectation of y. Thus, j inverse times k times j inverse is equal to the expectation of y times the variance of y divided by the expectation of y squared multiplied by the expectation of y once again. These two expectations of y in the numerator cancel with 2 further expectations of y in the denominator, and we obtain j inverse times k times j inverse is equal to the variance of y. So under correct specification, we obtain a different asymptotic variance matrix than we did under potential misspecification. So if we assume that the model is correct, our asymptotic distribution, square root of n times theta hat minus theta naught, is normal with variance equal to the mean of y. But if we don't assume the model is correct, the asymptotic distribution is still normal, but the asymptotic variance is not equal to the mean of y. It's equal to the variance of y. So what's going on here? Well, if the data really did come from a Poisson distribution, then there's no harm in interchanging the expectation of y and the variance of y, because we know that they're the same thing. But more generally, for other kinds of random variables, we know that the mean and variance are not the same. In this example, the robust standard error is based on the usual large sample theory for a mean. If I hadn't told you anything about the Poisson distribution or anything like that, and I just said I'm going to calculate the sample mean of some observations, you could have told me from the central limit theorem that the square root of n multiplied by y bar minus the expectation of y converges in distribution to a normal with mean 0 and variance equal to the variance of y. What we find under the Poisson assumption is that we can replace that variance of y with an expectation of y. But that will give us the wrong tests and confidence intervals unless the mean and variance really are equal, which they would be under a Poisson, but not more generally. So if we assumed that the data did arise from a Poisson distribution, then the way that we should construct, say, a 95% confidence interval would be y bar plus or minus 1.96 multiplied by an estimate of the standard error. What's the standard error here? Well, the variance in the limiting distribution is equal to the expectation of y. So we would substitute a consistent estimator of that, which is y bar, and divide by n. However, if we do not make the Poisson assumption, then there's no reason to think that y bar is a good way to estimate the asymptotic variance, because there's no reason to think that the mean of y should be equal to the variance of y. So the standard 95% confidence interval for a mean that we know and love is not this one, but instead y bar plus or minus 1.96 times the sample standard deviation of y divided by a square root of n. So we see in this example that although the Poisson MLE approach is innocuous from the perspective of giving us an estimate of something meaningful, we're still recovering an estimate of the population mean. We understand what that tells us. It is consequential whether we believe this Poisson model or not for calculating standard errors. So if we want to play it safe, and we don't want to rely upon the truth of our modeling assumptions, then we should use the robust standard error estimate, which is constructed by not assuming that j is equal to k.